we can get started. So, hello everyone, once again. My name is Eric Wanjau. I am a Microsoft Learn student ambassador here in Kenya. We are very pumped to have you in our second session of Machine Learning Foundations. So in this session, we cover something about classification. So as you'll see, classification is a form of machine learning in which you train a model to predict a category or class to which an item belongs to. So in this session, we'll be looking at some of the classification techniques and then finally narrow down to support vector machines. So once again, welcome to our session. If you have any questions, please type them in the chat if you can access them. And also, if you cannot, we'll have some time in between where you can put on your mic and you can ask your questions. Yeah, so that's it. That's all from me on my end. So we'll start with a small introduction to the topic by Sandra McKenna. She will introduce herself, and then we go to a Python walkthrough of a lab, and then we'll wrap it at a walkthrough session using R code. So yeah, I think that's it on my end. And without further ado, I present to you Sandra McKenna. So Sandra, the floor is all yours. I'll leave it to you. Thank you so much.
Hi Eric, thank you for the intro. I'll just ask you to share the slides, please. Yes, they're now clear. Sorry for the background noise. The weather here is not really good. So today, like Eric said, we'll be talking about classification in machine learning. So just to introduce myself, my name is McKenna Sandra, and I'm a research assistant at the Data Science Center for Machine Learning and the Center for Data Science and Artificial Intelligence. I'm also a Microsoft Learn student ambassador. So today we'll be looking at classification, which is a machine learning. It's a supervised machine learning technique that predicts a class. So for example, trying to classify whether an email is spam or not spam, or for example, given a few features of maybe what different types of dogs have, you can be able to predict the species of a particular type of dog. So we mainly have two types of classification. That's the binary classification, in which you're trying to predict one of either two classes. So that's usually like a yes or no situation. Then we have the multi-class classification, which involves predicting one of more than two classes. For example, maybe in the case of maybe like a tree species or dog species, where we have more than two possible classes, maybe a dog could, there are more than two classes that are possible. So the first, there are a couple of machine learning algorithms, classification algorithms in this area of classification. So we have the KNN, we have the logistic regression, random forest, decision tree, we have the SVMs, and we have the naive Bayes also. So the naive Bayes algorithm is a classification technique based on the Bayes theorem with an assumption of independence among predictors. So in simple terms, the classifier assumes that the presence of a particular feature in a class is unrelated to the presence of any other feature. We also have the KNN, or in full it's called the K nearest neighbor. So it is an algorithm that fares across all parameters of consideration. It is commonly used because of its easy interpretation and low calculation values. So like you see that if for example, we take K as 3, we look for the nearest neighbors of the particular data point we want to classify. And after we calculate the distance between it and its neighbors, we do a vote, and the class with the highest vote is where we'll most likely classify now that data point. Then we have logistic regression. It is used in classification in situations or scenarios where the output is a discrete value. For example, like whether an email is spam or not, or hello, can you hear me? I hope you can still hear me. If you stop hearing me at any point, please let me know. So like I was saying, there's logistic regression, where the scenario is where the output is either a 1 or 0, or yes or no. It's more used in yes or no events. For example, if a student is likely to get admitted into a university or not. We also have the decision tree. This creates a training model which you can predict a class by learning the decision rules which are inferred from the prior data. So like here we have a simple decision tree which can help you now finally classify or get the exact class or class label for your data, your input data. And we have the random forest, which is an ensemble of decision trees, usually trained with the bagging method. So in simple, this algorithm creates multiple decision trees on data samples and then gets the prediction from each of them and finally selects the best solution by voting. So it merges the decision trees together in order to get a more accurate and stable prediction. So like you can see, it's a bunch of decision trees put together. And now today we'll be focusing on the support vector machines. In short, is referred to as SVMs. So that's an algorithm where each plot of data item, we plot each data item as a point in the n-dimensional space, and n is usually the number of features, which with the value of each feature being the value of a particular coordinate. So then we perform classification by finding the hyperlane. So like for example, in our diagram there, the hyperlane would most likely be the one that you can see separating the orange and the green classes. That's the hyperlane, also referred to as a decision boundary, because a hyperlane is actually a decision boundary that helps to classify the data points. So it separates the two classes. So our objective is to find a plane that maximizes the margin. That means it gives a maximum distance between the two classes. That is between the data points, that's the orange and the green. So we're looking for a plane or a decision boundary that will maximize the distance between those data points of those two different classes, so that when we have a future data point, it can be classified with more confidently. So the dimension of the hyperlane will definitely depend upon the number of features. But beyond 3 features, it's usually very hard to visualize the data pen, the hyperplane, because in our case we only have up to 3D. So once it's 4D and beyond, that is very hard to visualize. So we have margins. We have like I've said, the margin is now the distance between the two classes. So our aim is to maximize that distance. So we have mainly 2 types of classifiers that help us do that. We have the hard margin classifier. It usually optimally separates the data very strictly. The hard margin classifier is optimal in the sense that it separates the two classes while maximizing the distance to the closest points from either class. So it tries to, in the best way possible, to create a very clear, distinct separation between the two classes. So the hyperplane from the hard margin classifier separates the two classes by maximizing the distance between them, and now in such situations, the hard margin classifier is usually better used, or can only work really well when data is completely linearly separable without any errors or any outliers. So now sometimes we have outliers in our data, and it cannot be possible to perfectly linearly separate them. And the decision boundaries of the hyperplane that is obtained using now the hard margin classifier will not generalize well with the new data, and this will affect our accuracy. So in such a situation now, that is when we would use the soft margin classifier. So using the soft margin classifier, we kind of loosen the constraint and allow some of the points to be on the wrong side of the hyperplane. So in that way, we are increasing the accuracy of our system. So we also have different kernels. So mostly kernels are usually used in a case where, like I've said, the data is not linearly separable. Like, for example, you cannot use a straight line to be able to clearly separate the two classes. So in such a case, that's when kernels come in. They help us to be able to draw better decision boundaries, or planes that can separate our classes. So the plane does not always have to be straight. It can be of different forms. So the SVM algorithm use a set of mathematical functions which are defined as kernels. So kernels are actually similarity functions, and there are a couple of them that different SVMs use. So the function of the kernel is to take a data as input and transform it into the required form. So these functions, or these kernel functions, can be of different types. They can be linear, nonlinear, polynomial, sigmoid. It depends. And there are actually a couple of kernel functions that are available and can be used. There's the Gaussian kernel, there's the polynomial kernel. There are quite a number of kernels that are used, but one of the most common ones is the Gaussian kernel, polynomial kernel, also the linear one. So to be able to, if you would like to find out more, there's so much content about different types of kernels and when they're used and the equations. I didn't want to go so deep into the equations and how they look like, because this was just a basic introduction, but there's definitely a lot more that can be said in terms of the types of kernels that are available to be used now in the SVMs. So with that said, I'll ask Eric to continue on, and he can add on as he shows us now an example, a real example, and we can look at how. Thank you.
Yes, hello. Hello.
Hello,
Yeah,
Eric.
Wanjau. Oh, okay. So, a bit of introduction. My name is Eric Ouma. I'm a student at Academy. I'm already a student. I'm also a Microsoft Learn student ambassador. So basically, I'll be giving you some presentation of. Let me present my screen so that I cannot be confused. Yeah, so I'm giving a little bit of presentation on support vector machines, some basic code with Python. So I'll be doing this for around 30 minutes. which means I'll not be going deep into some of the details. So kindly just be keen and follow along. Meanwhile, if you note anything or you have any question, feel free to post them in the chat section, as was mentioned earlier. So, getting started here, maybe most of us, as we've been told by the first speaker, SVMs are used in classification to predict categories. So basically, this code will demonstrate what has been presented in the slides. So the first cell here, in the first cell here, this is some simple code to help you collect data. So let's say you have some data in Google Drive. So you can just put the link here, link to the drive. So you can link to the drive here and then it will be downloaded. So yeah, personally already downloaded the data, so I have it. So sorry, using Collabs. So Collabs is a platform meant by Google for doing such work. So this is a Jupyter notebook basically that's online. So we also have the one provided by Microsoft, which is online. It's called onlinevisualstudio.com. So, but I'll be using Collabs for today. So here's my data. So if you want to view your data, you come to the left panel and you click on this folder icon over here and you'll be able to view your data. So next now, we'll be doing some configurations and of the things we're going to use. So here we are importing the warnings. What this package does is you'll realize most of the times, those of you who have worked with Python or I think other programming languages, there usually these warnings which are given when you execute code, let's say feature warnings or deprecation warnings. So this is basically a way to filter out those warnings so that they're not displayed. So you can also specify the warnings that you don't want. For instance, let's say if you don't want specifically you don't want feature category warnings, so you can just put here.
Eric Ouma. Hello, Eric. Eric, we can't hear you. Hello, Eric.
Hello.
Oh,
yeah,
hey,
hello.
Hey. Yeah,
you can hear me.
Yeah, we can hear you now. Could you do us a favor and maybe share the Collab link so that anyone who would want to follow along can do it at their own pleasure. Maybe could you share the link via our chat? That would be so awesome.
Yeah, I'm doing that. Let me do that right now.
Okay, thank you so much.
Where did you guys stop hearing me?
When you're saying about configuring, maybe for their errors, something. Yeah.
Okay, so I'm putting in the chat section. Can you see my screen?
Yes, Eric. We can see your screen. Yeah, we can see your screen.
Thank you. So basically, in this cell here, over here, we're doing configurations of some of the languages we're going to use. So the warnings basically is to filter out some of the warnings, for instance, deprecation warnings and feature warnings. So I'll remove this for now because I don't have the warnings. So this is matplotlib. Matplotlib is a visualization library. So basically here in this line where we are saying matplotlib inline, just telling matplotlib to plot or to show all the visualizations within this Jupyter notebook. And now let's get started with the important part, I would say. So I was familiar with pandas and numpy because those are the most common data science libraries. So sklearn is a machine learning library called scikit-learn. So it has very many algorithms, but the one we'll be focusing on today is SVM. So basically you can import it from a scalan, import SVM. So if you're working locally, you'll have to install all these packages from PIP because they don't come by default. But in Collabs, these packages are installed by default, so you don't need to PIP install them. And then over here, we are loading our dataset with pandas. So right now, so we're loading the CSV file which contains our data. And yeah, over here, we're previewing the first few lines of our data. Using with number of unique values in our column. So this is the dependent column that has our classes. So we'll be checking how many classes we have. So let me just run this. This is some of our data. So this is the first 5 lines of our data. So we have 4 features. We have the leaf width, we have the leaf length, we have the trunk girth, we have and the trunk height, and then our dependent variable is the tree type. So from what you can see here, we have class 0, 0, 1, 2. So basically we have a total of 3 classes. So as you can see, the problem we are solving here is a multi-classification. It's multi-classification because we have more than 2 classes. It's not binary. We have more than 2 classes. And so just to mention, for those of you who might not be aware, as you can see, this is data that has gone through cleaning and some other processes. So as you can see, because there is no missing data over here, the dependent column, I believe when this data was originally collected, these values were strings, like the tree names, for instance, cedar, fir, or whatever, and then they were encoded. They were encoded into this number so as to present those classes. So this, if our CSV file, if the CSV file we are using will have been in this format, basically this is what we will have done using these libraries here. So we'll have used the label encoder to encode our classes from categorical variables to numerical variables. So as you can see here, this is an example of categorical variables. So using the label encoder, we can convert to variables. Oh, sorry. Comment this line here. Yeah, we can convert them to. I think I need to comment out there. Right. Yeah, we can convert them to. Can you guys hear me? Yeah, we can convert these values to categorical variables. As you can see here, we have all this number of categorical variables that we've converted to numeric variables. So basically, that's what this data went through before it became in this state. So next, we'll be checking the features we are having. So this is a method. This is a method of that we use to leave out some columns so that we can get the ones we want. So here we are getting the features. We are getting the features and using this method. Using this method over here, we are collecting our labels. So we are basically, as you can see here, this dataset tree is a pandas data frame column. So we need to convert it to an array for us to use it. So there's also another alternative of doing this by saying I believe it's set. So you can say values. Yeah, this is another way of converting a pandas column to an array. And then yeah, we'll be plotting them so to see how data is distributed. And so if we run this cell, this is what you see. So this is the distribution of our data. So as we saw earlier, basically we have 3 classes over here. This is a plot. So we're plotting the leaf width as the leaf length versus the leaf width. It's very difficult to work with multi-dimensional data. And also, as you can see here, I tried to plot only the two features and left out the other two features because it can be very difficult to plot data that is past 3D. Yeah. Next here, we'll be taking a look at how it is distributed. Basically, it's the same code one above. What it does is just we have features from leaf to trunk. In this column, I will be taking a look at the variables. So one thing you need to know as a machine learning engineer is that when you collect data or raw data can have features or columns that have a lot of correlation, which is not good for a machine learning model. So basically, these are some ways of taking a look at the correlation of data, some ways of trying to reduce the number of features that you want to pass to your model, so as to give your model an easy time of learning. So those of you who have done some mathematics, I think you understand correlation and what these numbers here mean. So basically, the leaf width, of course, is highly correlated to the leaf width because it's the same thing. So it has a correlation value of 1. And yeah, all this. So the more the value tends to go towards 1, the more the correlation. The more the value tends to be negative, the lesser the correlation. So from here, our features are okay. They are not really, we don't have an issue with correlation which can affect our model. So next here is where we'll now be building our models. So we imported the SVM from Skyline. So this is the code that we use to create a model, a machine model. So basically, you call svm.svc, then you pass in the features and the labels. So the first model that we're creating, we'll be using the first two features. So we'll be using the width and the leaf length. So yeah, this is the and then these are the labels over here. And as I mentioned above, so this is our model. So it's as simple as that. So you pass in your features and you pass in your labels, train Y, and then you run your model. Yeah, so as you can, so our model has already been created. So yeah, basically this is the accuracy of our model, 93.5%. So this doesn't really matter because this is basic introduction. So most likely the model is overfitting or it's underfitting, and so the accuracy doesn't really matter over here. I'm just trying to show how you can, print out the accuracy of the model. So next over here, we'll try to visualize how the support vector machine has categorized. And yeah, as I mentioned earlier, I hope most of you are very conversant with Python and NumPy. So, but if you don't understand anything of here, you can head to the definition of these libraries, of these various libraries that I'm using here, and you'll get a clearer explanation of what I'm doing over here. For example, mentioning a way of concatenating column vectors, sliced column vectors, yeah, and all that. So over here,
Hello, Eric.
Yes.
You are breaking up a bit. Maybe could you please repeat from the previous cell? You are really breaking up. Maybe from the previous cell, yeah, from that cell.
Oh, okay.
Yeah, please do. Thank you.
So am I clear? Can you hear me clearly?
Yes. Now I can hear you clearly on my end.
All right. So over here, we'll be building our first model using two features. So the leaf width and the leaf length. And I'll mention later on why we chose to use two features over here and not all the four features. So don't worry, I'll mention that in the end. So basically here we are picking out our first feature from this leaf width column. And then we're picking out a second feature from the leaf length column. And then we are combining them into one called the train X. And then these are our labels. Remember, we had already converted labels to an array, so just assigning it to a new variable train y. And then this is the method that we use to fit a model. So basically, most of the scikit-learn algorithms usually use this method, .fit. So svm.stc, then you pass in your features, and then you pass in your labels. So this is the method that is used to train. This is the method that is trained or to build your model. So we call it model underscore leaf. And then this here, we're trying to get the accuracy of our model. So I would say this is not how it should be done. Actually, as you can see over here, you're supposed to score the accuracy of your model using a separate data that was not part of the training process. But because we didn't have much data here, so I didn't split our data over here. So I'll just be using the data that we've used to train our model. But this is not how it should be done. Let me emphasize that never try to get the accuracy metrics of your model from the training data. Make sure you have split data that you use to get your accuracy. I hope that's clear. So next over here, we're trying to visualize how the SVM has categorized our data using this plot. So it will be a scatter plot, but we'll be coloring the sections. We'll be coloring the various sections of the data that we have. So let me just run this data. Let me run this. So you can see over here, we have three classes. We have this class. We have these three classes given these colors. I think this is red, this is green, and this is purple. And as I think Sandra mentioned earlier, the support vector machines have various kernel methods which come in very handy in making the hyperplanes. So we have those which are linear and those which are not linear. So as you can see over here, it's obvious that the kernel that we're using is not linear, because as you can see, we have this sort of curved, we have these curved boundary lines that are separating our data. So let me change something over here. So then, if you need to change the kernel you're using, you can just pass in this method here. Use a linear kernel, and then so note that this boundary lines currently are curved, not really straight, but you realize that. So depending on your interest, or depending on the data that you have, that will determine what kernel you're supposed to use. So for this case, yeah, that's the linear. So next, so this cell here is similar to the cell above that we've changed the features we are using. In the cell above, we were using the leaf features, the leaf width and the leaf length. But over here, we'll be using the trunk features. So that is the trunk girth and the trunk height. So it's the same thing. We're picking our features from the data frame, and then the labels. And then over here, we're fitting our model with the new features. So we're using the same labels. Labels haven't changed. They're still the same labels. And so basically, this code does the same thing as the code above. The only different thing is using. So as you can see, still we have three classes over here, and the SVM has done a pretty good job of classifying our data. So it's not the same as the one above, but at least there is some using two features. So next, so I'll go through this very fast. So as Sandra mentioned earlier, working with multi-dimensional data can be very difficult, and especially plotting it. But there's a way around this. So in machine learning, we have something called principal component analysis. So yeah, so you'll realize the support vector machine, as we are plotting over here, if you can look at these plots over here, you can see that I can only plot 2 features, and the maximum you can plot are 3 features. That is, but with principal component analysis, what it does is that it reduces our data from this n dimension to a lesser dimension. So, for instance, our full data set here has 4 features, but using principal component analysis, we can reduce this data to a lesser dimensional, dimension, retaining the same information that the data had originally. So you've reduced the dimension of the data, but you still retained the information that the data had originally, so as not to interfere with the model that will come as a result of that. So basically, I'm using PCA because I want to use all the 4 features now. The previous 2 models we've been using 2 features. So right here I'll be using all the 4 features. So PCA is also available in scikit-learn. So you can import PCA from this method, imports PCA. And then over here, we are passing our features to the PCA method, and then we are defining the n components over here. I think more about this you can get from scikit-learn documentation. Especially, it's very important to understand this parameter over here. It can give you a lot of problems if you don't understand how it works. Yeah, you can get more explanation about that from the documentation. So here we are transforming our data to a lesser dimension now. So basically, we are converting it to a 2D dimension from 4D. I mean, just the same as the previous times. Now we're creating our model, but now we're using all our 4 features reduced to 2-dimensional data over here. So as you can see, we are passing PCA 2D. We're using the same labels that we're using. And then over here, we are plotting. And we're preparing to plot how this appears. It's the same as the one that was above. And yeah, so as you can see over here, it's almost similar to the ones above, 3 classes, and it's if you compare to the graphs that was almost the same thing. So I need to mention that when you're working with PCA, principal component analysis, you have to use the linear kernel. You have to use this when you're working with the principal component analysis. If you don't use that, you'll get into some trouble, which you can find out about from the documentation. Yeah, so that's all about creating models with SVM. So just to wrap it up, let me mention some things. So some of the advantages of support vector machines are that they are memory efficient, and as Sandra mentioned, I think she mentioned something about it. They are not affected by outliers, and we'll get more about, and I'll be telling us more about this in this next cells. So some of you might be wondering, so when am I supposed to use an SVM? Because we have very many classification algorithms. So on what cases am I supposed to use a support vector machines? So support vector machines can come in very handy in scenarios whereby your data has a lot of outliers. Another case that you might find it important to use support vector machine is when you have a high feature to row ratio. So like you have very few rows. You have very few rows, but a lot of features, like more than 4 features or very many features. So a high feature to row ratio. So that's another case where you'll find support vector machines come in very handy to use. And just to explain why support vector machines are very efficient, they're not affected by outliers. So I'll be plotting this diagram over here. Let me just explain what it does. So over here, I think this was mentioned by Sandra. So the goal of a support vector machine is basically creating a hyperplane that supports our data, that separates our data so that they can be classifiable. So the black line over here, the black solid line over here is our hyperplane, and these dotted lines over here are the lines that are cutting across our support vectors. So if you can see, we have dots that are bigger than the others, I think if you can see my cursor, those dots that are bigger than the others. So these are the support vectors. So these are the vectors that our SVM model has used to build the hyperplane. And so this tries to explain why it's coming very handy with memory efficiency. Because as you can see, it used very little data in building our model. Not saying that it considered the other data irrelevant, but as you can see from here, it used very few vectors in building our model. So that's one of the reasons why support vector machines are very memory efficient. Another reason why support vector machines are very, to explain why support vector machines come in very handy when your data has a lot of outliers. So as you can see, our hyperplane is built with the data. The point at which our hyperplane is built is far away from what I'll call the outliers, because as you can see, let's say for instance, this data over here is an outlier. Let's say if you can see my cursor, that is, let's say this point over here is an outlier. So there is no point at which our support vector machine will be affected by that data point, because the goal of the support vector machine actually makes it go away from such kind of data. So support vector machines are really come in handy when dealing with outliers, because they're not quite affected by outliers. Yeah, so this is a 2D plot of this is a 2D plot of the hyperplane, and that tries to get them more efficient, and they build another way of plotting the support function plane and the support vectors. So you don't need to addition all of this. Actually, this alternative method is available from scikit-learn documentation. This link over here is the most updated and the most efficient one, efficient way to plot the hyperplane. And, so something that Sandra also mentioned is that when you're dealing with multidimensional data, it can be very difficult to plot your data or view it, and support vector machines come in handy in such scenarios, especially by making use of principal component analysis. So looking at cases, for instance, where we have nonlinear data, so that is data that cannot be separated by linearly or by a straight line. I wish I had an image that will explain this, but there are cases where, if you look at, for instance, if you plot your data and you try to estimate by yourself the decision boundary, it appears to be something sort of a circle. So let's say there's data that has surrounded another data. I want you to look at that scenario whereby you have data points that have surrounded other data points. So kind of we have a circular decision boundary. So it can be very difficult, or it can be very, it can be challenging to get a decision boundary in such a scenario. But support vector machines come in handy because with the kernel trick, they're able to change such kind of data to higher dimensions, so that they are linearly separable. So you can read more about the kernel trick and the mathematics behind it. So just to explain that, I'll do a 3D plot of one of the video. So as you can see over here, this is a 3D plot. So this is the hyperplane in 3D over here. This is a hyperplane in 3D over here. And this explains why support vector machines are also come in very handy when dealing with nonlinear data, because in some scenarios it might be very difficult to classify such kind of data. But with the kernel trick, this data is converted to a higher dimension, which makes it linearly separable. This one over here, it's kind of complex to understand it. It's so difficult. So what next after you trained your model and now you want to use it or take it to production? So you pass your model and the file name. So they'll be saved over here. In this case, they'll just be saved over here. If you can see this file over here. And then to load your model file, you just call the same library joblib.load, and then you pass in your file name. And you can use now your new models, your loaded models, to make predictions. For instance, if we have this over here, you can use this model over here that loaded to predictions. Find the predictions of this new observations. If you can see over here. Yeah. So we get tree A and B. So the leaf model classified tree A as 0, the trunk model as 0, B as 0. Yeah, I don't know that. What are the names of these trees, but yeah, that's it. Your model file, and allow me to conclude over here. I think I was clear, and yeah, for those who are interested in learning more about support vector machines, there are a lot of resources online. Thank you. Back to you, Eric Wanjau.
Hello, Eric. Thank you so much for that Python code walkthrough, and also for putting in the work to do some PCA. I know that was not planned for, but thank you so much. It really helped drive some points home. So yeah, I cannot really thank you enough for that. And maybe you could interact with people in the chat, maybe share resources, and maybe answer some questions that could be there. So guys, if you have questions, please put them in the chat. Yeah, so thank you, Eric and Sandra, for that first session. Now I will kindly introduce Ian to take us through the R code walkthrough. Yeah, so guys, if you have any questions, please type them in the chat, and Sandra and Eric will get back to you. So Ian, the stage is yours.
I think now it's okay. I don't know if you guys can see my screen.
Yes, finally.
Yeah, you can see it.
Yeah, we can see your screen. You can see your IDE. I mean.
Oh my.
Yeah.
Yeah. So
Yeah.
I apologize for that. Technical issues. So I think most of what I was going to present has actually been said by Eric and Sandra. So I don't think this session will be so long because yeah, I think everything has been said, but I'll just add on a few. Maybe I'll show you how you can implement the same using R. Yeah, so we've already been told what support vector machines are, and yeah, so I think maybe what I'll add on is maybe the kernel functions. Had somebody asking about the kernel. Yeah, so in SVMs we have something we call you have your data set, and then you have something called a feature space. So in the feature space, that's the place whereby we're actually going to be implementing the hyperplanes and actually doing the classifications. So for you to transform your data set from where it is currently, from your data set, and then you transform it to the hyperplane, what's actually used to do the transformation is what is being referred to as the kernel function. So, for example, if your data set is maybe nonlinear, whereby you can't do linear classification to the data set, if the data set is two-dimensional, meaning that maybe it contains maybe two sets of classes, but you can't really separate them linearly, you have to use something like something more complex to separate the data set. You have to transform the data set from 2-dimension to 3 dimensions so that you can have more flexibility in terms of classification. Now for the transformation from 2D to 3D, that's where we use kernel functions, and an example of kernel function was given by Sandra, the likes of RBF, Gaussian radio basic, Gaussian and others. So yeah, so for this session, the packages that I'm going to be using in R are tidyverse and E071. Yeah, so and to install them, you just run this code, this code that I'm highlighting right now. Yeah, you install tidyverse and also install the package E071. And to confirm if the packages are installed, you can just run this line over here, and you'll see it should give you following output. So if we run that, and you'll see the output. My computer is a bit slow. Yeah, you'll see that you won't get an error message over here, so you know that you have the package, and also when you run this, you'll also see. Okay, sorry for that. You'll also see. You won't get an error message over here. So after loading the data, the packages which you're going to be using to do to build our SVM, we have to load the dataset which you're going to be using for this session. And the dataset which you're going to be using for this session is similar to the one that was used in Python, the one about classifying trees. Yeah, so this is how we load our dataset from R. And notice what is here is actually the path to the dataset. For example, this is the path where I stored the dataset, and I'll give you a link as to where you can find this dataset which we used for the session. Yeah, and to see what's actually contained in the dataset, we run this code, because you have to first of all understand the data that you're working with for you to actually start doing operations on it. Yeah, so as you can see, we have something called the tree type, and the tree type is actually it's a value from 0 to 2. So 0, 1, and 2. So we have tree type 0, tree type 1, tree type 2, and the classification is actually based on the leaf width, leaf length, trunk girth, and the trunk height. So based on the values of the leaf width, leaf length, trunk girth, and trunk height, we actually get the classification of the tree. So yeah, so that's the data set which you're going to use. And from the results, you can see that the tree has three classification categories, 0, 1, and 2. And the features or the characteristics that are used to actually do the classification are as highlighted below: the leaf width, leaf length, trunk girth, and trunk height, meaning we have 4 features. Yeah, so to get a better understanding of our data sets, and in any machine learning approach, if possible, it's better to visualize the data. So the code over here actually plots the data. It actually plots the leaf features, where X is the leaf width and Y is the leaf length. So first of all, you start with the leaf features. So we first of all do away with the trunk features, but first of all, we look at the leaf features. And yeah, so when I run this code, you'll be able to see the table that I just show you. I just shown you as a plot. Yeah, and you can see the different colors represent the different classes. So for tree type 0, we have red. For tree type 1, we have green. And for tree type 2, we have blue. And as you said, in this data set, we have some extraneous variables, the outliers, as I had will call it. Yeah, and as you can see, there's this value over here, which is a red value in the blue, a green value in the red, and a red value in the green. And we're going to be talking about those and how to go about them. Yeah, so that's how we do our plot using ggplot. The function which you're going to be using is ggplot. Yeah, and this is how we plot in R. So I won't go into details about that, but there was a session Eric did on ggplot. So if you really want to understand what's happening, you can refer back to that. Yeah, so from the plot, we see the 3 groups, which I just said, the 0, 1, and 2. And yeah, so similarly, we go back to the trunk features, the trunk girth and the trunk height. So we also plot them to see how it looks on a plot, and you can see classification based on trunk girth and the different classes. You can see the green for type 1, the red for type 0, and the blue for type 2. Yeah, so visual representations are always best because they help you really understand what you're doing with your data set. Yeah, so we see that there are some extraneous elements, but for the most part, the features of the trunk girth and trunk height can actually allow you to predict a tree type. Meaning, if you're given a value that lies in maybe the red region, maybe you have a trunk girth and a trunk height, when you plot it on the plot, you find that it's somewhere here, you can confidently say that it's a type 0, and if it's here, you can confidently say that it's a type 1 because this data set is clean. But in real world scenarios, the data set isn't normally separated as such, because in real world scenarios, the reds will be in the green and the green will be in the reds and the blue. It will be a mix-up of some sort. That's why we need SVM to actually find an optimal way of classifying the features that one is given. So what is our training goal or objective? So suppose you have a new tree specimen and you want to figure out the tree type. Yeah, so the first option will be what I said earlier on. If you have you're given a value of trunk height and trunk gap, all you need to do is just to come and plot manually. So if you plot a value over here, you'll just look at the trend around that area, and then you'll see that it's a tree type 2. So that's one of the approach that you could do. And alternatively, because this is just a data set that we are using to show you how SVMs actually work. So alternatively, you could use SVM to predict the tree type, and which is actually more advisable because you'll actually get a more accurate prediction as compared to just inferring using a plot that you made on using a point that you made on such a plot. So as the SVM actually uses features and labels to provide for the known tree types, and this is achieved by creating hyperplanes. So the hyperplanes allow us to predict which tree type and which tree type a new specimen belongs to, given values of the leaf and the trunk measurements. So so to implement this, we create an SVM that actually is based on leaf features alone. So there's something that I also need to mention. SVMs are actually binary classifiers. So that's why when it comes to classification, we only choose 2 features at a time. And for maybe in cases where there are more features, maybe like more than 2 features, we can actually do binary classification in a creative way, meaning you can perform repeated binary classification between the maybe 2 or 3 classes, and you will actually get an accurate classification. So this VM function is found in the package E1071. And to see how the functions is actually used, you can just run this line of code. And you can actually see a description of SVM. It tells you that it's used to train and support vector machines. Okay, sorry for that. And below here, you can actually see the syntax. The syntax as to how we use SVM here. So you can see that you have our input variable X, Y, scale, the data, and the arguments are actually quite well documented in R. So you can actually just go through the details that are provided in this window on the right, and you can actually know how to use it. So for this case, we'll use this syntax as VMX is equals to that, Y is equals to that, and the data set. So in this case, the X actually represent the features. So the features are actually, for example, the leaf features are actually the leaf width and the leaf length. And the trunk features are actually the trunk girth and the trunk height. So, sorry, not that. Okay, So X actually represents the features of class matrix, meaning that for the variable X here, it has to be a matrix. And matrix, I'm sure most of you are familiar with matrices. And Y actually represent the labels or the classes. So in our case, the labels will be type 0, type 1, and type 2. So it's actually quite vital to note that we are going to be using these 2 classes, the matrix and the factors. So matrices, I'm sure most of you are familiar with, but a factor basically is used to categorize data. And a good way of visualizing this is maybe we can say that we have a factor A, but the levels of air are oxygen, nitrogen, and carbon dioxide. Or you could say that you have a factor, a fruit, but the different type of fruits are actually the levels of the factor. So we categorize data using factors in R. Yeah, so we to fulfill the conditions of having a matrix and also having a factor, we have to first of all check the type of elements that are in the data set which you're going to be using. The data set which is this data set over here. So to do that, we type this command, and you can see, first of all, the data is stored in a data frame, and the leaf width, leaf length, leaf girth, and the trunk height are actually numeric, and the tree type, which is our classifying, which is actually our classifying argument, is actually an integer. So we have to convert it from an integer to a factor and convert the data frame, which is actually a data set, into a matrix. So first of all, if we create the first SVM, which is only based on the leaf features, which are the leaf width and the leaf length, we'll have to create a new variable that contains only these two features. Remember that in the dataset that we are using, we have 4 features, but for demonstration purposes, we'll only use 2. And once we create this new dataset, we then convert the new dataset which we've created from a data frame to a matrix, so that it can actually satisfy the condition of X being a matrix. And we'll also have to convert the labels into factors, so that we can actually satisfy the condition of Y being a factor. Yeah, so conversion, and this is how we do it. Okay, so in this line of code, we create the new data set, which we call XLeaf data, and we take the tree data, which is actually the data set with 4 features, and then we select the leaf width and the leaf length, the 2 features which we are going to be using. And then once we select them, we convert it to matrix using this bit of code as matrix. So once I run this, okay. Once I run that, and then I look at the class of the dataset I just created, you'll see that the class output is actually a matrix. So the new dataset which we've created, containing only 2 features, the leaf width and the leaf length, is actually a matrix. So to see the new subset which you created from the tree data, remember a subset is just a section of a bigger data set. So it's a subset of tree data, because tree data had 4 columns, but our new data set, XLeaf data, as you can see, only has 2 columns, leaf width and the leaf length. Yeah, so once we do that, we are done. We've satisfied the first condition of actually having it as a matrix. So the second thing will be converting the tree type, which is actually our classification criteria, into a factor. So this is just a way of we just pass the tree data set, which is actually the original data set with 4 columns, and then we convert it into a factor using this line and using this syntax. So once we do that, let me run this. Once we do that, we can check the class. Remember, in R, for you to access a specific column, so for example, in this data set of ours, see that there are 4 columns. To access the tree type column, we use the $sign, which is actually called an accessor. So this line of code over here just checks the class of the tree type column, and you can see that the class is actually a factor. And when you check the column, you can see that the column is just made up of the different levels, which are actually the classification criteria. So level 1, level 2, and level 3. So now we are ready to run the function SVM based on the leaf features stored in the new variable XLeaf data, and the labels saved in the variable tree data, specifically the column tree type. So we use our SVM. So Similarly, using the argument which we saw, which we discussed earlier about SVM, so we have our X, which is the data set, which contains the features, which is XLIF data. And then the Y is the classification criteria. So I'm going to call it a classification of criteria, which is the tree type. So, and the type is classification, and the kernel which you're going to be using in this case is the radial basis function. Yeah, so once we run this, and yeah, so once we run that, we get the output. Just have this output here for fun, but you can see that you followed everything. You can see that it will print out our SVM model dubbed SVM leaf data is lady. So the SVM model which you created, this SVM model which you created over here is actually called SVM leaf data. It's a support vector machine. Yeah. So at the beginning, we mentioned something to do with hyperplanes, and to illustrate this efficiently, we are going to create a grid of data points within the feature space to represent the different combination of leaf width and leaf length, and color the new data points based on the predictions of our SVM. So in this case, we are going to compare the old classification values and the new one, and then we see how our SVM model has done. So this is how we do it. We get the grid. We're running these two lines of code. Yeah, so we create a data frame with columns leaf width and leaf length. We rename the columns from variable 1 to variable 2, from variable 1, variable 2 to leaf width and leaf length. And so you can see the grid which we created is actually made up of two variables, variable 1 and variable 2, which are actually the leaf features. Yeah, so for every new point in the fine grid leaf, we're going to predict the tree type based on the SVM which we just created. So this is how we do the prediction. So just to check the output. So you can see that we have the variable 1, which are actually the features. So the first feature, the second feature, and then the prediction which our model is making. Yeah, so once we do that, we can see how many entries there are per prediction. So as you can see here, we just have zeros, which is not really helpful. We want to see if there are other predictions which were made. Yeah, so once you run this line of code, you can see that in 0 there are 3,000 entries, 1 and 2 has 3,520 entries. So once we have this, the predicted values, we can now create a scatter plot that contains the details which we need. Yeah, so it's this piece of code looks complicated, but it's not. It's all about ggplot. Yeah, so once you run this, you just run it. Static must be length 1 or the same as the data. Okay. Okay, just a moment to see what the error is. X leaf width, Y is the leaf length, color is equals to the prediction. Okay. Let me run this. I'd actually checked this code before the lesson, so before the session, so I don't know what changed. Run it again. So yeah, the problem was the previous sections below. So this is how we do it. So basically what this piece of code does is it actually plots the predicted values, and actually plots the regions, the regions that are actually divided by the hyperplane. So as you can see, the region is the place which is colored. So we have three regions: the blue, the red, and the green. And as you can see over here, we have the predicted values, which are actually for class 2 are the blue dots, class 1 are the triangles, and class 0 are actually the circles. Excuse me for a minute. I'll be right back. Apologies for that. Yeah, so I can continue. So we have the classification and the black region, the black boundary lines that you can see on the plot are actually the hyperplanes that are dividing the the three classes which are actually predicted. So from the graph, you can see that the three faint colored zones are the SVM's classification prediction based on the leaf features, and the hyperplanes are the thick black boundary lines. So the first approach of actually, because at the end of the day, when you create a machine learning model, you have to actually find a way of actually testing how well it performed. So the first test, you can just do it by using your eyes, by observation. And we can see that classification has actually happened quite nicely because the predicted values actually lie in the corresponding regions, because the green triangles actually lie in the green, and most of the majority of the blue rectangles lie in the blue region, and the red circles lie in the red region. But just to have a more accurate method of doing this, we can make two observations from this. So first of all, it's what I've said. Our original data points have been classified correctly because majority of the classifications lie in the correct region. But you can also say that there is some level of misclassification because there are some reds in the green region, which means that some type 0 trees have actually been classified as type 1s, and some type 1 trees has been classified as type 0. And this region, I don't know if you can see my cursor, but you can also say that some type 0s have been classified as type 2 trees. And to actually determine precisely if our classification is accurate, we have to test the level of accuracy by determining the misclassification rate. So to do this, and as Eric said, we need to have a test data set. But in this case, for illustration, we'll use the original data set as our test data set. So we run the prediction again. And so we run this again, but instead of using the data set which we created, this data set, let me show you just a minute. This where is it? Yeah, this XLIF data, instead of using this data set which we created, which is actually a subset of the original data set, we use the original data set which was called tree data. And so from here to actually evaluate how our model has performed. So we use our original data set, we predict values based on our original data set, and then we see the prediction. And this output command in R actually gives you the first few rows of our column, and you can see that the leaf width, the leaf length is that, and our prediction is this. But because we want to do a comparison of the test data set and the one which you predicted, we have to compare the prediction of the two data sets that you use. So we have to compare the prediction that was predicted when you used the original data set, the prediction that was made when you used the other data set, which was a subset of the original data set, and then compare the two values and see what was our misclassification error rate. So to do that, we have to join. You have to join the two errors, the two prediction. And we do that like that. See, you run this, you see that now have two different columns that have been added to our output. So we have the prediction and the actual value. So in the first case, it was class 0, and the predicted value was 0, and the original value was 0. So in this class, the second time, our prediction were wrong because the class is 1, but it actually the class is 0, but it actually predicted a 1, and so on and so forth. So because the entries are too many, remember these are just the first six rows. We have to find a way of actually doing an arithmetic comparison between the two columns to see what our misclassification rate was. So to do this, we create a table of predictions showing the misclassification rate. So see over here. So the table looks something like this. Yeah, and to actually, because this table doesn't really give you so much information, we calculate the mean to see the misclassification rate in terms of a percentage. And we see that we had a misclassification rate of about 6.5%, which actually, as Eric said, it's actually it's more, in some cases it's actually preferable to a misclassification rate of 0%, because a misclassification rate of 0% may mean that our model has overfit the training data. So it's actually quite, it was actually quite okay. So because I didn't want this task to be one-sided, I decided that for the section of the trunk features, remember we just used the leaf features for this session. So for the trunk features, I decided to task it as an exercise to you guys. Maybe you can follow what we've done and actually come up with a model, an SVM model that classifies using the trunk features. Yeah, so in a nutshell, that was my presentation, and I hope you guys will look at this, because the procedure is the same and the steps are the same. It's just that you'll have to really go through what you've done and then maybe come up with something similar, but using now the trunk features instead of the leaf features which you used. Yeah, so in a nutshell, that was my presentation. And if there are any questions, yeah, you can ask me in the chat. So thank you. Eric, I hand it back to you.
Hey Ian, that was really awesome and informative. Maybe before I release you, I have one question. So you created like a finite set of values, and then in there, how do I put it? There's this place, I think you created a new data set, and then I think you predicted it's treated. Is that what you did?
Yeah, that's exactly what I did.
Okay.
Yeah. So
no, just continue.
Yes. So what I did, okay, let me see if I can trace that line of code. Yeah, so I created a finite set from the original data set, which actually I used it as my training data set, and for comparison I compared it with the original data set, which was the original data set, which was this. Okay, where is it? Which was the data set which had 4 columns. Yeah, so because remember, when it comes to ML, you have to actually have 2 sets of data set, a training data set and a test data set, to determine the accuracy of the model. So in this case, that's the approach I used. Yeah, so yeah, I hope I answered your question.
Yes, Ian. It now totally makes sense. So yeah, man, I just want to say thank you so much for taking your time to do this in R. And for the R guys, so I'm really appreciative of that. Thank you for the effort. Yeah. So now for now, I'll just maybe leave it to the audience. Maybe who has a question to maybe either unmute or write it in the chat. So I'll give out a few minutes to the audience for questions. So guys, it's your turn. Please, if you have any question, this is your turn. This is your chance. I mean. Okay, so I can see Eric and Ian have put in the data sets that they used in the chat. So if you'd want to follow along, maybe at your own time, please see our chats. We'll also be sharing this through the email shortly, and also the recording of this session. So maybe at this point, I'll invite Eric or Ouma, maybe something you want to add before we wrap it.
Yeah, sure. Yeah, let me thank Ian for his art session. Actually, yeah, it's making these sessions more diverse so that we don't just limit to Python. And yeah, I also like to urge our audience that in machine learning, expertise comes with practice. So some of you might have been in this call and maybe you feel discouraged. Maybe some of the things you are saying, you're wondering, you've never seen them before. Yeah, it's not that we are some special people. It's practice, it's practice. Someone like myself, I've been doing machine learning like for over an year right now. So yeah, it's practice and keeping on learning and doing projects. So one thing I will urge you is to understand yourself, know what kind of a person you are. Are you a video person? Okay, are you a person who studies then works on project, or you learn from projects? Like there's the top-down approach where you start by working on projects, then now you go to understand the mathematics of machine learning. But there are those who prefer understanding the mathematics of machine learning, then now they start working on projects. So find out what kind of a person you are, then yeah, you'll be good with time. Thank
Yeah. So thank you, Eric, for that great piece of advice. Uh, really appreciate it. Sharing how you did it. And also sharing with us that yeah, it takes time, and sometimes it takes time, and that's still okay. So yes, as Eric said, please take the sessions, doing some work, put in some work, and we assure you in no time you'll be up to speed with these concepts. So once again, Eric, I'm very thankful for doing the Python walkthrough. I think the majority of the people here are Python people. So thank you for really doing such an amazing walkthrough, and yeah, we hope to see you more in our session. So I'll also give it to Ian. Ian, maybe some last words. I don't see Sandra here. Maybe so, Ian. Maybe some last words for the R community. And you also didn't say that you're an organizer at DekutR, Ian. So yeah, so Ian is an organizer at DekutR.
Yeah, so I think maybe the technical hitch at the beginning of the session really threw me off my game. So that's why maybe I didn't give out my title and all. But yeah, I'm an organizer at DekutR. We work with Eric, organizing meetups. And what I can say is that when it comes to issues, machine learning and AI, it's always best to take a practical approach, because the theory behind it at some point may seem tough, but once you see somebody who has implemented or a project that has been done online and you can actually follow it, because guys out there are actually doing projects and really giving out some good documentation as to every step of what they did. Yeah, so if you can maybe heavily rely on the practical aspect, once you see something that you don't know on the practical, you come back to the theory. That approach worked for me. But yeah, as Eric said, don't give up. And yeah, it may take some time, but once you start understanding the concepts, once you start understanding what kernels are, what hyperplanes are, it stops becoming a monster, and it becomes something that you actually enjoy doing, which is actually the goal of such sessions. And if you have guys like Eric Ouma and the rest, the Sandra and Eric Wanjao, who you can actually maybe contact to and ask them questions, maybe where you're stuck, maybe you can reach out to them. I believe all of us should. You have no excuse of saying that you didn't get the necessary resources to learn. So I think that's my take from all of this.
Okay. Also, Ian, thank you so much for doing it in R. And for also that very informative session. You really went to the nitty-gritty. So yeah, thank you so much for that. So guys, I'll maybe ask Ian and Eric, please, maybe you could type in your contacts, and maybe if anyone who wants to reach you can do that either by mail or the contact that you give. So I think I'll wrap it at here. My name is I was Eric Wanjao. I was the moderator for this session. So guys, we are really thankful for everyone who took their time to attend. We really will not do it without you guys. So man, you're the best. Yeah. So and maybe just take this up this time to tell you at least now you have different, how do I say, different approaches you can either take, the Python path or the R path. So yeah, you don't have to be, we are not limiting you, we are giving you a lot of options or on how to tackle machine learning. Yeah, and we hope this gave you a really good introduction and got you up to speed with what classification really does, and in particular how to handle classification problems using support vector machines. So we'll be doing more sessions on this. So I think next time we'll go to neural networks. So and we'll still do them in Python and R. So yeah, be ready for some really exciting uh, problem solving using neural networks. And as Ian and Eric said, there's so many tutorials out there. So just taking some time, have a good attitude, and be willing to put in some little work. And in case of any questions or any resources that you need, please do contact Eric, Ouma, Ian, or me, or even Sandra. So on behalf of the Microsoft Learn Student Ambassadors here in Kenya, I want to wish you a good night, a good evening, and happy learning, and all the best in everything that you do. So I think I'll wrap it up there. Maybe anyone else want to say anything? Yeah, this is your chance, but I think we'll end machine learning foundations classifications at there. So thank you so much, and see you next time.